So today, primarily, section 5.3, and then to some extent, there's a bit from section, I think it's 11. Let's see here. Section 9.2. So what we're interested in is a little bit more statics, but before, when we did statics, we were considering balancing of torque and balancing of force. This time, we're moving beyond just sum of torques is 0, sum of forces is 0, and considering what happens within a given solid, for that matter, a fluid, when forces are being applied to it from the outside. The things that we're interested in are what are called stress and strain. The general equation for elastic behavior of solids is like this. Sigma is equal to some modulus of elasticity times epsilon. This one right here is what's called stress. This right here is called strain. And this right here is the modulus of elasticity. Okay. Now, I've gotten a hair ahead of myself by introducing this equation because we have to A, know what these three things are and what they represent, and B, understand when this equation can be applied. It's not an always applicable equation, but it is applicable for quite a variety of stuff. For example, it is applicable in like biomechanics, in finding out how much stress your bones can take. Not only this, but a related equation which tells us what the maximum amount of stress is before you start to shatter or break. And it could be anything from a civil engineer trying to figure out how much force the bridge that they built can take, meaning how big of a truck can drive across it, to a doctor trying to figure out how much force is needed to, like break some bone, and therefore how much force we should not exceed when we're setting up like a traction device. Or not just bone, but also tearing muscle and so on. Okay. So in general, we need a definition of what is strain and what is stress. So stress, sigma, just represents how much force per unit of area is being applied to an object. Now, some of you may be familiar already with the concept of force per unit area. You may have encountered it elsewhere. Does anybody have any term that means force per unit area that is not just stress? Sorry? That's the unit. Okay, I heard from pressure. Yeah. So pressure has units of force per unit area. as it turns out, what is pounds per square inch? When do you usually encounter that unit? It is used in hydraulic presses. Probably the most common experience people have with that one is when your tire is running a little flat and you pull out the tire gauge and you stick it in the tire and it tells you the tire pressure. And the units is usually in pounds per square inch because the manual for your car says it needs to have this many pounds per square inch for this tire. And it's usually something like 30, depending upon what kind of vehicle you have and what kind of load you expect and so on. What tire manufacturer you used. Okay, so pressure has the same units, pounds per square inch, or in SI units, newtons per square meter, which is called the Pascal, by the way. Okay, that has the same units as stress. Now, a moment ago I think I said coincidentally it has the same units. It's actually not entirely coincidental because one type of stress is pressure difference on the walls of something. So for example, if you have a tire or a balloon, you have some pressure from the outside acting inward on that balloon. Everywhere. But you've also inflated it, so there's also some interior pressure that acts outward everywhere on the balloon. This says in, not M. I-N, the interior pressure. All right, so one type of stress is difference in pressure. This is what's called bulk stress. It's the difference in pressure inside and pressure outside. And it doesn't necessarily matter which order you take them in. It just tells you in which direction is this balloon going to have to react. And how does the balloon react? If you apply more pressure from the inside than outside or vice versa, what does the balloon do? Either does this or contracts. All right? So what is the property that describes whether it inflates or contracts? Well, that's the strain that's been put on the balloon. So the bulk strain is given by something like this, where the V represents volume. All right, so you inflate your balloon, you have it at equilibrium in the air. Maybe it's a helium balloon. You release the helium balloon. What happens to a helium balloon when you release it? Initially it goes up, right? Then what happens? Yeah, what happens to a helium balloon after it's gone up into the air? Eventually it pops. Why does it pop? It does not get too hot. The air pressure decreases as the balloon rises. And so that means that you have more pressure inside than outside. So the balloon starts to expand, expand, expand. Okay, and so then eventually you reach a point where you're nearing the upper edge of the atmosphere. And the balloon is like this big around, and it's supposed to be like this big around or something. Eventually it bursts. It can't handle this amount of strain anymore. thing bursts. There's actually, if you want, you can go onto YouTube and find this. There's people who have done stuff like attach a GoPro cam to like a helium balloon and then just send it up to watch what happens. There's one fellow who was out of Purdue University that did this, and he basically was able to figure out how high the elevation was and everything. He got it up to the upper edge of our atmosphere, basically. You can't go beyond the atmosphere with a balloon, because what is making the balloon rise is the difference of pressure above and below the balloon. Once you get to a point where there's no more pressure below the balloon or above it, there's no more rise either. There's no difference between those two. This is what's called the buoyant force, and that's introduced actually in sections 9.1 and 9.2 and so on. All right, so this is one type of stress, one type of strain. There are actually three types, or three common types of stress and strain. Bulk is one of them. The other two are shear and tensile or compressive. All right. So what does shear stress represent? What does shearing mean? It basically means layers of the material are trying to somehow slide against one another. All right. So you have a solid object like your ruler, or like one of these pieces of paper. Shearing, when I tear the piece of paper like this, I'm shearing it. If I take the piece of paper and I twist it around like this, this is also a type of shearing. I'm somehow making layers twist or slide against each other. All right? And the equation in the linear regime is the same. We use a different number for this modulus, and this take on slightly different meanings. All right? Let's say that I have, where's that ruler? Here's my ruler. So let's say that I have a ruler, I hold it straight up like this. It's basically straight up and down. One version of shearing is to cause it to bend like this. This is involving some sort of a shearing stress and strain. Okay, and you can imagine that it's possible, though very difficult with something that's this flimsy, to shear it in such a way that the whole thing kind of leans from base to top. So you go from some cross-section that looks maybe like this to a cross-section that maybe looks more like this. All right, this is a type of shearing. Now, the strain that you get from this type of shearing is measured by determining how much delta x, how much shift you have, say, from top to base versus what height you have from base to top. All right? So shear actually, I'm just defining strain at the moment. All right. So what about the stress? How do you get stress out of this? How do we get stress out of this? Well, it's going to be a force per unit area. So one way to look at it is I've sort of like planted the bottom of this here and I apply some force up here somehow. So I have some total amount of force that's being applied. Alright, so sigma S is how much force for how much area. What area do I use? What area is useful for the, yes?
Wouldn't it be the area between like, the initial function?
Okay, so you could shade in like a triangle that we've drawn here and figure out that area. That's a good guess. It's not the one we want, but it is a good guess. It's a very good observation that there is an area bounded by those. That said, the actual area that you usually want has to be some area bounded within the material itself. That's kind of true for all of these. This one right here, the area in question is just the whole surface area of your sphere. For the other two types of stress, you don't want the whole surface area. It's usually some sort of a perpendicular area, or sometimes a sort of parallel area. Okay? So, in this thing's case, the area in question, you have a face here, you have a face here, and you have a face up here. So it's going to be one of those three faces. And shear is kind of the weird one, because the other ones, like this right here, you have a volume, you have a complete surface area, the area is well defined, the stress is well defined. In the case of tensile and compressive, as we'll see, again, the area is well defined and what's happening is well defined. There's one thing that means a tensile stress. There's one thing that means a compressive stress. Basically, it means if I took the ruler, if I pulled on both ends, or if I pushed inward on both ends. Those are the tensile and compressive ones. Shear, because there are so many different ways that you can shear, you kind of have to define the area from context. Basically, am I shearing it like this? Am I twisting it? Am I trying to punch a hole through it? That's also a type of shearing. So, in this thing's case, the area in question actually ends up being the area of this top of the ruler. So it's this really small cross-section area. All right. If, as another example, so this would be like area of top. As another example, let's say that I have like a wall like this. I want to go punch a hole in the wall, like with a hammer or something. It's like as a part of a job site cleanup or something, demolition or the metaphor. So I'm going to punch a hole in this wall. I'm going to do it by hitting a hammer into it. All right. The force again is reasonably well defined. It's going to be whatever force I have for my impact. And that, again, may be changing with time, and it may be a very short amount of time during which the impact happens. So we might use like the average force during impact. What area do I got to use for this item, this hole, if you will? So let's define a few things. The wall will be like this. It has thickness, we'll call this, maybe this is like y, here's x, so this would be z. And then I also have the hole itself, which has some radius r. how would I find the area, the relevant area for this hole? To figure out how much stress I put. And the strain in this case is it breaks. Okay. The sigma is the force from the hammer divided by the area. What is the area going to be? We'll assume for simplicity that somehow this hammer is able to make a perfectly circular hole. Okay, so what would that be? What's the area of the hole? A hole is a three-dimensional entity, right? Okay. There is a little bit of method to the madness in figuring out this area, right? We could say, oh, well, the area is pi r squared. That's the area of the circle. It turns out that's not the area we want here, though. Here's the little bit of method that you can try to use to figure out what kind of area should I need to account for. Suppose that I have two things that I'm going to punch a hole in. Both of them are made of the same material. Maybe it's like a piece of plywood on the wall. But in one area, we use a 1/4 inch thick piece of an 1/8 inch thick piece of plywood. In another area, we have a 1 inch thick piece of plywood. Which one's going to be easier to knock a hole in? The 1/8 inch or the 1 inch thick? Which one? Easier, 1/8 inch, right? You can, without any particular training or anything, you could probably walk up and like kick the 1/8 inch thick, and if you kick it just hard enough, you'll get a hole in it, or shatter it, or whatever. If you walk up to an inch thick piece of plywood and just simply kick it, and you don't have any specialized training, anything like that, you're not necessarily going to put a hole in it. You might put a dent in it, but you're not going to put a hole in it. Okay, so we expect thicker to be harder to get through. And if you're capable of kicking a hole in the 1 inch piece of plywood, imagine that you've stacked like 20 of them, and now try to kick a hole in that. It's not going to be very easy. So we expect the thickness of this thing to play somehow into how easy or hard it is to get the hole. Therefore, whatever area we have, because this term is determined by how hard we hit with, this area has to somehow take thickness into account. And so the only area for this circle that takes that thickness into account would be the lateral area. Right? If I take this thing, all my markers have migrated. If I take this thing and I redraw it, just looking at the piece that I've cut out, is basically a cylinder of some sort. Not a very good cylinder, but hopefully you have the idea. So the relevant area is the lateral area of the thing. All right, and so A, in this case, how do you get the lateral area of a cylinder? So you want to remember? Yeah? 2 pi r times z. Okay, in other words, you take the circumference of it, that's your 2 pi r part, and you multiply by how thick or how long or how high, whatever you want to call it, the cylinder is. That was your z part. Good. All right. So that's your area in this thing's case. And so on. Okay, the last one that I have to put up here, because it's not up yet, is for tensile and compressive. Alright, this is the case where you've taken your ruler, you've given it a pull like this, you're trying to pull it to make it longer, or you're trying to push it together to make it shorter. Alright, so your ruler, or your beam, or whatever, might be drawn something like this. Alright, and so the force would be like this. So I've drawn a compressive force in this case. Sigma, in this case we actually have a special modulus, which is called the Young's modulus. So this is for tensile. Alright, and so in this case, sigma, force per unit area, is the force we've drawn here times this cross-section area here. Which I'm going to label as A sub x for A cross-section. So the cross-section area, if you're not seeing where I've put it, it's just the area of this face that you're applying the force directly to. Alright? And it works the same if you're stretching the thing. So if I'm trying to stretch this by applying forces like this, and again, we're using that area there. Alright, so in some ways this one's the easiest one to deal with. You just figure out what face is perpendicular to the force that's being applied, or what cross-section is perpendicular to the force being applied, and that's the area you use. Alright, now with the exception of this brief example where I make note that you can break by shearing, I've stuck to what is called the linear regime of material response. This equation is valid in the linear regime only. Materials actually go through quite a few different regimes, one of them being the linear regime. Looking for a certain graph that I want to draw. It turns out, though, that if you apply some amount of stress to material and therefore allow it to undergo some amount of strain, that you don't just get a linear response the entire time. So this right here is usually some constant for the material that you can go look up for any given material, and that means that this equation implies a linear relationship. In actuality, though, this marker is dry. In actuality, you plot stress versus strain, or strain versus stress. Okay. Let's say that this is, for example, a delta L over L. What you end up getting is a graph that looks something like this. So for some while, the graph is pretty linear. This is what's called the elastic region, or the linear region. sometimes regime, sometimes regime. Doesn't matter. And this happens up to some point, after which you usually get a little bit of a fall off, actually. And then from there you get kind of a slow rise, maybe a little bit of wiggling, this kind of thing. And then at some point you usually end up breaking. And anything beyond that, you've already broken it, there's nothing more you can do to it. So this right here is sometimes called the plastic region or regime. And then this right here, where it breaks, is called the fracture or break point. All right, this equation applies here to the linear part of the graph. And for what it's worth, this equation is very similar to another equation that we've seen earlier in the semester, which is called Hooke's law. I'm sorry, this is going in the area you guys can't see. I'll move it over. So here's Hooke's law, if you've forgotten. It says that some constant times a change in length, or a spring, is equal to the force applied. Now this right here, it turns out, is very much like the equation that we have here. It turns out that a Hooke's law spring just is a tensile or compressive object upon which a tensile or compressive stress has been placed, and which strains by changing its length. The strain in this thing's case, I guess I never wrote it here, is delta L over L naught, where this length right here would be your L naught length. It changes by stretching out by some small amount or compressing by some amount. The Hooke's law spring, the same thing is happening. It's just that our effective Young's modulus for a spring is very small in comparison to the Young's modulus for even something flimsy like this ruler. In fact, this equation, in some sense, comes from this equation, although I think that they found this one first, historically. Okay. The K in your spring, the spring constant, force per unit stretch, very nearly corresponds to the modulus of elasticity here. In fact, there are some additional terms muddled into it, such as some cross-section area for the spring and some initial length of the spring. Implication, among other things, the longer your spring is, all else being equal, the smaller your spring constant will be. The bigger your cross-section is for your spring, all else being equal, the stiffer the spring will appear, the larger the spring constant will end up being. All right, so what is the modulus of elasticity? It's a sort of direct measurement of the stiffness of some object that you're trying to stress, that you're putting a stress on and attempting to strain. All right, so the larger this number is, just as the larger this number is, the more force you have to apply to get the same amount of strain. The larger the number is, the stiffer the object is. Okay, one last point here on solids, which is the breaking point. In your book, and I think this is in section 5.3 of your book, there should be a chart which tells you the values of the modulus of elasticity, maybe for all three moduli, depending upon the material. Now, if you have a solid object, then all three of these things will have a modulus of elasticity for them. If it's a liquid, then there's not actually going to be much in the way of a tensile or shear modulus. You mostly just have a bulk modulus. Liquids can shear easily. Tensile, I suppose you could put something that somehow compresses it, but you have to somehow contain the liquid, and so you still have ultimately a bulk pressure on it. This is unlike with a solid, where if you just push on the two ends, it will try to compress until you break it. Okay, so item 1, there's a chart of values for your modulus of elasticities in your book, and you'll need it when you're doing the homeworks. Item 1B, because it's related to the homeworks, you can finally now do the hammer and nail project problem from chapter 8. Because it turns out that the hammer and nail problem, what you're trying to do is make use of your tensile elasticity of the nail. Alright, so you'll want to look up what is the Young's modulus for the nail, or maybe it's given in the problem. And you want to look up the area across which the force is being applied, which is basically the cross-section area of your nail, in order to solve that problem. Item 2, what about breaking stuff? I outlined how you could figure it out for something like a wall, but I only outlined it. So let's describe it a little more explicitly. In the case of a wall, you have some force that you're applying to it. That's usually a given. Maybe you have to find it, but usually it's a given. You might, for example, take a hammer, you slam it into the wall, the hammer had some initial velocity, it comes to rest, it takes some amount of time to do this. From that you can find the average force. That's using conservation of momentum, or using impulse and momentum, or using Newton's second law, variously. I've told you how to find the area. In this thing's case, you got to find the lateral area of the cylinder that you're punching through the wall, or the lateral area of whatever you're punching through the wall. It could be a square-shaped hammer, I suppose. What I haven't told you is the piece that links these together. All right? The equation that you want to use for braking still looks kind of like a sigma equals something times strain, but it's really sigma equals sigma max. Okay, sigma max is what's called the maximum amount of stress, or the braking stress, that you can apply to an object. So for any material, there's a maximum amount of force per unit area that material can take before it breaks. And that maximum amount is different for each of these three types of braking. This right here, what does braking look like in a bulk? Well, it either means you ground it to powder, you're compressing something inwards, or you you've shattered it completely. Or in the case of the balloon, it pops, it bursts. All right? So any of those are sort of breaking for both. For this thing, it can mean you've punched a hole in it like this, or it could mean you've torn it. So again, with the piece of paper, if I take a piece of paper and break it by tearing it, that's also breaking, and that's a shear type of breaking. So you'll want to look up the maximum shear stress for that. For tensile, which is perhaps the most useful one to those of you who are planning to go into either biomechanics or the medical field or etc. Breaking, in this case, is not the same as a snap. That's actually still a shear. This is more like you put somebody on a traction machine and you put too much traction on it. Something's going to sort of snap this way, pull apart. There's some maximum amount of stress that you can put on different materials, be it bone, be it muscle, be it a tendon, etc. Usually you go pretty well below that, by the way, when you're doing a traction machine. But at the same time, what's the point of the traction machine? Why do we use a traction machine? Somebody has broken their femur, ouch. You want to get the bone to set correctly. What's the main problem with setting a bone in if your femur is broken? You have a lot of muscle in your thigh and it pulls together, and so instead of setting like this, it'll try to set like this. And so the traction is to counter the fact that the muscles in your leg are naturally trying to pull this thing together. And so it's like you're putting a counter tension on it so that it can set correctly. Well, how much counter tension do you have to put? Well, obviously enough that it overcomes the muscles contractions in your leg. But if you just say, okay, I'm going to go to a very high amount so that the leg muscles cannot possibly do this, you also risk tearing the leg muscles, which doesn't do your patient any good. And it looks like we're out of time for the day. So next time we're going to do statics in fluids, and in particular we're going to do Archimedes' principle.